So recording, all right. So what I was just talking about, length of vector. If you have it in the form of angle and distance, then that's relatively simple. The magnitude you've given is the length. But now that if we're having the component-wise representation, so we have if this is v, then we know what's v1 times I, and we know v2 times j. Then how to calculate the length. And in 2D, this is something you already know. It helps if we call this C, this we call A, and this we call B. And then we know that A squared plus B squared is C squared. So the length from Pythagorean theorem is square root of A squared plus this was plus B squared. And something that, well, if you do the calculations, that becomes obvious. But this does, as long as we're having a basis where all the basis vectors are at right angles, this just generalizes into an arbitrary number of dimensions. If you wanted, you could do the work in such a way that we're having a three-dimensional vector that points, let's say, this point here. It's a little bit messy to draw, but it is intended that it goes out in a point that's above this one. And the projection here would be here, and so on. And if you calculate first, we could reduce this component-wise so that we calculate first one of the projections. So the projection here is that. And if we calculate what that is, okay, we can use a Pythagorean theorem to calculate, for example, using this triangle. Now we have that component and we have that component. So if this is A, B, and C, so we want to calculate D here. Well, let's say it is. Let's actually name them. So if these are X, these are Y, and these are Z. So this component will be V1. This component is V2. This component is V3. And this one, let's say C and D just so we could here immediately see that C is V1 squared plus V2 squared. Hopefully this at least somehow looks like it's visible to people on the internet as well. And then this one is now a triangle where we have C and V2. So V2 is over here. And then we can say that D is, using Pythagorean theorem again, it's C squared plus, yes, that should be V3 plus V2 squared. And if we put this in this C2 squared, we notice that squared plus V3 squared plus V2 squared. Okay, and this should be squared. So those cancel out. So we end up having just the components if you go through the way of going up the dimensions. So in result, any number of so the length of a vector which we can mark that way, or in this case the norm, if we are really proper, this is the second norm. That's something that will be mostly skipped on your education later on the bachelor side. So that essentially means that way going by right angles. So that is square root of the sum over I. Actually, these parentheses are superfluous. So that notation is we have the sum sign. This is the capital Greek sigma over I. If I was really proper, I would here say that that I equal from 1 to 3, for example, for 3-dimensional. And what we do, we take the ith component, so we 1, 2, 3, and square it, and then calculate the sum, and take the square root of that. So that's what that notation means. We'll have more about some notations later on. We're going to need those when we talk about series. Okay. Any questions on that? So starting with the simple things today, then let's go on to the mean value theorem. Reminds me a little bit about the squeeze theorem. Let's try finding it from the Moodle. We should have already the slides here, and we do. So mean value theorem. So okay, this is the theoretical way of putting it. So function f is continuous on a closed interval from a to b, and is differentiable on, well, to different a to b. So there are a few different notations how to mark if the endpoints of the interval are included or not. So I like to use those square brackets, and if they're the wrong way, and that means the endpoints are not included. But you may have also seen another notation. So so I'm using C belongs to the closed interval. A to B is how I personally write it, like this. So, and then if we have D, that's on the open interval, it's like this. Or this is equivalent in some notations. So some people mark this with the regular bracket, regular parentheses. That so this 3 lines means it's equivalent to. Or I do actually more commonly use this logical double-headed arrow. So the first one, C, is on the square brackets inside, means that it can be A or B or anything in between. And the open interval means that it can be anything between A or B, but not A or B themselves. And here we have a case where the function is continuous. So we do have some kind of it should be a function, so and it has a value and is continuous on some interval. So this is our function, and okay, it goes. Now it can be variable in here as well, but it doesn't need to. And there's a it starts increasing here. So maximum of the differentials here and goes to 0 about here. So we're having a derivative of something like this. So this is roughly its derivative. And what does that mean? It says that if we put just the secant there or slope, then this direct oh snap, I should really bring a ruler with me. So this direct line slope must be found at least somewhere over here. It's probably somewhere here already, but C must be somewhere in the interval anyway. Doesn't matter where. So one of the obvious points here is that I think it was next. So in Rolle's theorem, if those are the same, there must be a minimum or maximum on that interval. And again, this wrong way E means that there must exist such a thing. And this kind of rounded E means belongs to a set. In this case, the set is just a line of numbers on the x-axis, essentially. Well, we usually call it the x-axis, whatever the parameter is. It could be time. So let's have a function. This is just the square root of x. And we don't know what the endpoint are, but we require that it is larger than 0 or larger or equal to 0, so that we don't end up into funny stuff with the domains. So we mark the function there. So the derivative with the value of c is so that's the mean value theorem, and let's calculate what the values are. So after differentiating this square root of x, we get 1 over 2 to the square root of c. So we already substituted the value of c there, and then we substitute the b and a values. So square root of b minus square root of a, and then the difference. And what the next step does is that we assume that b is square root of b squared. So we substitute this what we have on the green box on the below. So, but the symbols are different ways. So usually we mark that formula that it's a squared minus b squared, but the symbols themselves don't matter. I probably should have used that on other symbols to slightly less confuse you, but we can use that even if we don't have the square. We can then just take the square root as long as the general format works. All right, so now we notice that we have a common term on both of the numerator and denominator. So the numerator goes to 1, and what's left is the square root of b plus square root of a on the denominator. Now we're next inverting both sides, so we can trace those equal signs as long as we need to, and we have 1 over 2 square root of c equals to 1 over the square root of b plus square root of a. Flip around, we get 2 square root of c is square root of b plus square root of a. Divide both sides by 2. So we can say that, well, okay, and take the square. So we get that c is the square root of every square root of b and square root of a. We could also calculate, say that a is square root of a squared. So the same thing we did with a squared minus b squared formulas here. So we could say it's like that. So if we want, so a is less than c is less than b, should be relatively visible here on the lowest line, because we know that a is smaller than b. Some manipulation here. Not too many glass eyes. But okay, now that we hopefully have everyone here, I wanted to take a little bit of time to ensure that. I have one question. How many of us does possibly want to start this lecture at 8:30 instead of 8:15? No one? Okay, a few hands. Who does insist starting on 8:15? Okay, in the future we're going to start 8:30. So I'll make a note on Moodle. Remind me if I haven't done so. But yeah, I'm also not exactly a morning person. Okay, another example. So this is closer to how we could use the mean value theorem to prove stuff. So we want to show that if sine x is smaller than x for all possible values of x that are larger than 0. Okay, so sine peaks at 1 by definition, so we don't need to consider, well, we don't really need to consider x values larger than 1, but just to keep on the period nicely, so from 0 to 2 pi. This is when we talk about only one cycle, we pretty often also write this with a capital S sign. Okay, mean value theorem. So what we're now taking is the sine x over x is the ratio between sine x and x. If this is smaller than 1, then we know that the value of sine x is always smaller than x. Now we add both sides zeros, so sine 0 is 0, and 0 on the denominator is also 0. And turns out that is similar format as our derivative. So this Newton's quotient or difference quotient, and but only when x goes to 0. And we can see that based on what it is like, it's cosine is the derivative minus cos. So yeah, cosine. So we know that it is a decreasing function in this interval. So this difference quotient is always smaller than the derivative sine if we put the endpoints on the derivative. So it ends up being still cosine c that caps what this difference quotient could be, and since cosine c is always smaller than 1, then we can follow through the inequality signs. It must be that the ratio is smaller than 1. And if we want to drive this home, multiply both sides. So we have sine x over x on one side, 1 on one side. X is greater than 0 by definition here, so we can multiply both sides. So we get sine x is smaller, or is less than x. Here's a slip I tend to do with Finnish. In English, we properly say
less than or less or equal than for the inequalities, but in Finnish it would be literally smaller than. And yeah, so if we think about unit circle radians, this should have been obvious, because can anyone say what's the graphical representation of this if we think about angle x as radians? So this is one part where radians are quite nice, because if we define the sine as a unit circle, I'll take a little bit of a shortcut here and just draw the first quarter. This is now not x. This is whatever axis we have. And we had the angle x here. And the height of this triangle, by definition, is sine x. And if we're using radians, when we're having a unit circle, then the length of this arc here is x. So sine x is this one, and x is the arc length. And essentially, what is sin x smaller than x means is that this height is always smaller than the arc length, which, now that we draw it that way, was incredibly obvious immediately. But worked only on radians, so the numerical value of the angle in degrees is of course smaller, larger, at least pretty soon. All right, so, and it actually reads it over here as well. Arc of the unit circle is always larger than the height of the point on the circle. I didn't want to make it too obvious. Yeah, we had these definitions. So monotonically increasing function, or in what our textbook calls increasing function, is that if fx2 is larger than fx1, then x2 must be larger than x1. Decreasing the opposite way, and non-decreasing, or occasionally if this is non-monotonically increasing, is that if a value is larger than the other value, then the function value at that parameter must be at least as large. And this is something that comes into the generalized MPT. And now we're doing this not with just values, but we're doing this with functions. We could essentially show that we do the mean value theorem for both functions f and g. Flip one of those around, and the b minus a's cancel out each other, and we end up getting this. And if we need to somehow figure out the ratio of these derivatives, now we notice that we actually don't, well, rough direction, if a and b are sufficiently close to each other and we can calculate the function values, we don't necessarily need to know what the derivatives of these functions are. Application on the next week. Okay, so that was about the mean value theorem. So just bit info dumpy, but that's it for short. Okay, that's pretty quick actually. Well, let's see. So higher order derivatives, here we have more examples. So essentially, the simple way of doing a higher order derivative is just differentiate it again. But in some cases, we can have formulas. So second derivative usually marked with 2 dashes and so on. But then important part, if you see superscript in parentheses, this means that it's the nth derivative. So it's not a power, so that's how we differentiate it in notation from powers. And all the different ways of marking your derivatives are equivalent with each other. And also notably on the capital D notation of derivatives, if you have a subscript with a variable, it tells that the differential is with regards to that variable only. If you want to use that notation, then you might be needing when we get to partial derivatives, which means that we have multivariable or multivariate if we want to use Latin functions, and we want to see how it changes on one direction only. And yeah, we have a few examples. These are directly from the textbook with some additional explanation, because the textbook does not really explain what it does there on the examples. We'll try general powers, and then general kind of a divisional quotient of the sign, which is a periodical function, and then we have the last one is an example of a really simple looking function that does not have an obvious formula for the general derivative. One thing where you can immediately see that we might end up having issues is that it has on the inner function, if we apply the chain rule, it does have a second power. So others have linear inner functions. So when we differentiate them once, the variable disappears, it's just constants. But on the final one, we end up having the variable there. It might not be trouble. We might just have an increasing power of the variable there. So we just need to use the multiplication rule as well. But in this case, it ends up having, yeah.
Can I ask that? Was that KTH?
Yeah, Kate. So K is if we mark this, we would mark so K is some number in the set of natural numbers. So K is 0, 1, 2, 3, and so on. And Kate is well, okay, not in this case, not 0. So it's actually in wait, I got it wrong. In Z plus. So 1, 2, 3, 4, first, second, third, and so on derivative. So any arbitrary, yeah, that's actually good reminder for all. When you use symbols, the proper way is to define what those symbols mean. So this is the standing for some integer derivative. There are also fractional derivatives, but we're not going to touch those on this course. Okay, so going on for the higher derivatives, so we offer power. Okay, we get first derivative is just n times x to the power of n minus 1. Okay, next derivative, multiply with n minus 1. N is a constant, so it doesn't affect here, and the power is n minus 2, and so on, so on, so on. And if you are familiar with combinatorics. Then on the bullet point after 3, this should look familiar to you. So it's a combinatorial, so how many combinations there are between n and k, and we can use the fractional. Is everyone familiar with the exclamation mark notation, which is the fractional? Good. And of course, when we get in case of powers, when we get a derivative that's higher than the power, then it goes to 0. So x to the power of 0 is 1. So when we have k equals n, so it still follows the formula, but then when we differentiate, well, okay, it is some constant, so it has n, the combinatorial of n minus n to k times 1, but then when we have constant, no matter how large it is, when we differentiate once, it goes to 0. Okay, simple deal. We can use the same method of looking how this goes. We're having a essentially negative power, and now we're having an inner function as well. We just apply the chain rule. What we get on the left side of that rightmost parenthesis is just a constant, so we can move it on the left side of our, if we use the d or d over dx markings here, we can move them over, so constants don't matter for derivation. Okay, we're still going to factorials, and we notice that what the n, okay, this is now the nth, so it's not actually k, it's marked with an n. Well, the sentiment is the same. So what we have there is that this -1 to the power of n tells us that when with even powers or even derivatives in this case, it is positive, and with odd derivatives we need to put a minus in front. Okay, we get the factorial of n, and then we get minus n minus 1 power there. So seems really straightforward, just need to notice the pattern there. So when we multiply a factorial with a the following number, we can just increase factorial by 1 by definition. And the minuses are not inside the factorial, so it's minus factorial of 3, not a factorial of -3. Okay, sine. Okay, we're having a periodical function, so by definition, first we get a cos ax plus b. Simple deal. Okay, cosine is minus sine, and again from the inner function we put the a to the front, so minus a squared. And we notice that now we're having this sine ax plus b again, so it's minus a squared to original function. Differentiate again, we get minus a squared times a times cosine ax plus b. So okay, we get minus a squared and the derivative of the original function, original derivative. So, and then when we go on, okay, it goes a to the power 4 times original function, differentiate again a to the power 4 to differential. If we go on, we notice that for even derivatives, we get the sines, and for odd derivatives, we get cosines. And this, on the bullet points, this is how you can tell that something is even or odd. So we define this n to be 2k, and when k is an integer number, then n must be always be even. again, if we define n as 2k plus 1, then that must be always an odd number, because 2k was always even, and k is an integer. So we could here notice a pattern, and this was one that I said it was a trap, because it is. So looks simple. We get just the general application. Okay, we have 2x and a half, so x goes in front, and we get minus half. Okay, we have the chain rule for the parentheses part, but we also need to have the product or multiplication rule here. So derivative of x is 1. So the first one here on the second part is derivative of x times the function x squared plus 1 to the power of minus half. Okay, then we get the other part multiplication rule, so x by itself and the derivative of this x squared plus 1 to the power of minus half. Okay, so we go there, and now we needed to use also the chain rule there. We get this part here. So here the x disappears, and we have just the so what we needed to also apply here was dx fg is f dash g plus fg dash. Okay, so now we notice here that we do have, if we take this x squared plus 1 to the power of minus 3 over 2 as a common factor, we get that it happens here x squared times plus 1 minus x squared times, so those x squared minus x squared cancel out each other, so it's just that. So here we might have a look, okay, there possibly is a pattern. So we had a similar here on the originals. Let's go on forward, the next small step, but then we have different multipliers, so it goes to minus 3x on the front. Okay, so that didn't quite work out the same at all, so it doesn't follow the pattern. And we go one more step, it goes even further from pattern. So at least to me, it's not really obvious what the pattern here is. So while in many cases, this book originally is made from the time when we used a lot of those handbooks. So we could learn, for example, my primary way of differentiating and integrating is that I check if the handbook has the formula. If it has, then I cite that I'm using formula from beta, page this and this, formula number this, and by this formula, the result of this integration is this. But it doesn't always work, so you also need to be able to differentiate yourself. Similarly, occasionally, now our current technology is a lot better. For example, from alpha can integrate and differentiate a lot, but occasionally you get weird results where our computer algebra system thinks that the best solution is use an infinite series, where it might have a bit more elegant solution. Okay. All right, so that was it. Only 1 hour. I'm now pretty much running out of material for this lecture, but let's see. That's not a really big problem because we can go on. Implicit differentiation. wait a moment, this should be in this lecture. So why it wasn't on the material? I'm using my old material, but then I'm just checking week 2. Okay, so let's see what's in this material. So I'll need to upload this. This is not uploaded yet. Apparently last time around we didn't have time to do this on the same week, so this wasn't on the same package. But this is this week's topic very much so. Now this is simpler if we use the Leibniz notation. Okay, so we know that derivative is the same slope of tangent of function. And now we're having things that are not actually functions. So this is a circle. So it's not a proper function. And okay, at plus minus 5, it does have only one value, but otherwise it scoops up and down. So it's yeah.
You got these slides on Moodle?
No.
Okay.
So well, just a second. I haven't really read this since last year, so there might be some errors that are not fixed, but editing mode on. And where's the correct folder? There we go. Now the slides are on Moodle.
Okay, thanks.
Let's just to prevent damage, let's take the editing mode off. Okay, so yeah. So now, if we mark this y dash is dy over dx, so essentially assume that y is a function of x and substitute that there, now we can start trying to differentiate this so-called function. It's actually two functions joined, if we want to go formally. So, for example, if we had y squared is x, now we know that there's this plus minus thing happening as well on here. So we'll now split it into two. So when we take the square root, we need to consider both the plus and minus options. So y1 is the square root of x and y2 is minus square root of x. And differentiating those, we get two options what the differential might be. Another way is that we just mark it this way. And now we can use this ddx as if it were some kind of function. So we apply the chain rule here. So we have inner and outer functions as well. So y squared, we consider y as a function here. So we get 2y and dy dx. And the derivative of x is just 1. And now if we still consider that the dy dx is some kind of function here. So that was the dy dx is the derivative of y, what we mark it. So, and we get that the other side is 2y dy dx, and the other side is the derivative of x, which is 1, and divide so that we get dy dx on one side, and we can tell that dy over dx is 1 over 2y. And now y was the function, so if we put the options we get, so y1 and y2, we get, so substitute minus square root of x and plus square root of x, we get the derivatives that way as well. So the non-obvious place here is that this dy dx here is not just marking a differentiation operation, but it is essentially just a mathematical function by itself. And when we solve what the mathematical function is, so we have now done the differentiation and divide both sides so that we only leave this dy dx on one side, we have a solution, what it looks like. And this explanation was way too fast, and this is possibly the hardest part we can do on derivatives. So we have further examples. So yeah, here's a graphical representation. That's a hyperbola, and these are the tangents of the hyperbola. I'll need to see if we have, yeah, here's another example. So we want to find what's the dy or dx for this nice periodical function we have here. We cannot at all solve for yx, so we couldn't do the previous trick where we solve for yx and then see what it goes using traditional algebraic solutions. So let's just differentiate for d by dx. Left side goes with the multiplication rule. I actually need to write this example open. Last year I was really in a hurry up with this. So with yeah, well, on the left side, derivative of y is dy dx. Yeah, and then I'll need to check this. Why did we get cos y there? It should be a. I need to check this. So this was on the wrong folder, so I didn't prepare for this week. Yeah, it should be. This is the same example as in the book, but occasionally sources do also have some funny stuff. And but yeah, the cos y is clear. Yeah, the cos y is the minus sin y. Yeah, so that's the right side. And then there's something funny going on here. Let's see if, okay, it didn't go on. I'll need to check this by hand and we'll do this tomorrow. Okay, one thing is dependent velocities. So we're having again a bit of a nasty formula here. So T is temperature, V is volume, and T is just simply constant when air masses move. And then the difference in, so we assume that for a short period there is no convection, there's no transmission of heat, so only convection. So heat moves only with the air. And then now we when differentiate by temperature, we can use formulas here. So this goes, the constant goes to 0, of course, and then the other part we're differentiated by volume over time. So depending on which one we do, when we differentiate t, it goes to 0 here, and then when we differentiate by volume, then the t is constant. We're leaving it as is because it's a multiplier there, and then we apply the power rule here. Okay, collect terms. So now we try to find the difference in temperature. It goes on one side. So what we have here is this is differentiated by t, and this is this same formula differentiated by v. We're collecting terms, so now divide everything by what's, so move these terms on the other side and divide everything by whatever is input for dt over d non-capital T. So t went over, and divide by that, we get t. Okay, here's -2, here's -1, so what's left is v to the power of -1 and dv. And how do we read this? Is that when volume changes, then by this multiplier we can tell how much the temperature changes. So temperature change is this multiplier, which was a multiplier for dry air, times T over V, current ones, and then volume change. I'll need to find some numbers. So with that, you could do also things like start plotting numbers that roughly an estimation. If we have 1 unit change of volume, how does it affect the temperature? And when we know the current temperature, current volume, then put the change here, change in volume, calculate this, and we can kind of take a step on the temperature side. So if we have a change of volume, how much would the container's temperature change? And this should appear sometime later as well. There's of course minor errors. So if you're familiar with Euler's method of numerically solving differential equations, we know that when we do just a linear approximation, there will be errors when we don't take into account the possible curvature of the model. And last year I had notes on this, so I did this by hand, but now I can't possibly remember where those are. I'm pretty sure they're not on the same folder. So we'll continue tomorrow. This is slightly complex topic. I want to show a few other demos as well. And I actually found some code that draws last week's engine demo. So this should help on understanding it as well. All right, well, way too fast today, but again, so now I know it's important. Next week I'll need to make more material instead of using my last week's ones. Any questions I can try to answer, especially the implicit differentiation is a thing I'll need to prepare myself slightly better because I haven't really done much on it in a year, so memories get slightly hazy. So this is mathematics is a skill you can practice. Unfortunately, I did not have very much time last year to practice, just going on with the topics. All right. One interesting discussion from yesterday. So there was a question about right-hand rules. So we have two different right-hand rules, or apparently two different right-hand rules. So what was the difference between this rule and the thumbs up rule? And it is just the amount of I need a marker. Amount of dimensions we take into account. So if you're having 2D vectors, so we're having on the board, well, for example, if we're talking about momentum, we're having a force that's affecting this lever, then if you assume that it's actually 3D, so it just has 0 component here, both rules, so which way is the rotation plus or minus, or which way, and then which way force points should reduce to this rule if you assume that this direction has component 0. So for example, tau is so if you add zeros to 2D forces, it should still hold. But when we're drawing, it is a lot simpler to keep the 2 dimensions. So we don't, in some cases, we can ignore some stuff and maybe use easier trigonometry instead of needing to use the proper vector path. All right. Anything else? Any questions at this point? I think I asked it already. If not, then this lecture's it. I'll need to remind myself that I'm going to check the implicit differentiation and either prepare a video on that or then present it tomorrow. But I'll try to keep the Thursday sessions slightly shorter. Okay, I can minimize Zoom so it doesn't go too late. And we also noticed yesterday that we noticed that some of these events are moving around. We're now on Wednesday the 9th. And next week looks the same, then looks the same. Okay, it's only after the midterms that we'll move into different programming altogether. But I'm not terribly happy about this. I'll need to ask people if we could not have a 4-hour lecture on Wednesday morning, and especially not so that we need to swap rooms in the middle. So keep an eye on this, and we did have one of these events. Okay, so if you see a red dot here, it means that there has been a change. So on this case, we're having a different room. But I'll try to remind you as well when we're a bit closer, because we're weeks away from that still. All right. So, okay, not calling it a day, but this lecture is more or less it.